going to talk about graph signal processing for other types of data, motivated by the same kind of modeling ideas that we develop. And with this, I'm going to conclude. My research overview, basically, I mean, I was introduced already. There's a Google Scholar link. I got my PhD from Arizona State University under Professor Anna Scaglione in 2020, and my thesis is titled Model-Based Machine Learning for the Power Grid. And there are two basic parts in that, in which I'm going to today talk about the graph signal processing for the power grid. I also briefly worked with differential privacy for advanced metering infrastructure. And as of now, I am interested in federated learning, threat models, and security. That's just showing a small diagram of what I do or did. With that, with that, in this talk, what are we going to talk about? What am I going to talk about? What is graph signal processing? So this extends the ideas from discrete time signal processing on to the ideas discrete time signal processing ideas to signals that sit on a graph. And why are we interested to use tools from graph signal processing for the power grid? Because the measured data from the power grid can be naturally thought of as signals on a graph, which is the infrastructure network of the power grid itself. And where else can GSP or graph signal processing be applied, and how can we do it? So I'm going to talk about two different kinds of data, social networks and financial networks. And the related publications to this talk are listed here. When I share the slides with you, you can have access to them. So first, let me start with the introduction. What is graph signal processing? As I said before, GSP extends notions from discrete time signal processing, or DSP, to analyze data that come from networks. So what happens here is the coordinate system of the data set is associated to a graph with vertex set V, an edge set, and a possibly weighted adjacency matrix. And so what graph signals are, they are vectors defined on the nodes of a graph, and it's a mapping going from the nodes of a graph to the real space, with n being the cardinality of the number of nodes in the graph. And here is a small figure showing how a graph signal can be expressed. And once we have defined what a graph signal is, one important concept is the graph shift operator. And what a shift operator does is it mixes adjacent nodes in the graph. It's a neighborhood operator, and the idea is to think of shifts as similar in the DSP notion of a time shift. So we are looking for an idea of a graph signal to be shifted in the graph. So that's a graph shift operator. So most commonly, the graph shift operator is the Laplacian, but the adjacency matrix and the others can also be used here. And now that we have defined what a graph signal is and graph shift operator is, what is the graph Fourier transform? So once we perform an eigenvalue decomposition of this GSO, or the graph shift operator, the eigenvectors from the graph Fourier basis and the eigenvalues are called the graph frequency. Now, what is this supposed to signify? So here is a small figure where I'm plotting the the values of the adjacent nodes in the GFT basis corresponding to different eigenvalues. So the larger the eigenvalue, the more is the variation in adjacent nodes. So this is sort of supposed to indicate the low frequency where the graph signal is quote unquote smooth, which means that the variation between adjacent nodes is not much, versus a high frequency where the variation between adjacent nodes is still quite high. And now that we have an idea of a Fourier basis and a graph frequency, we can equivalently define a graph Fourier transform. And that is defined here as it acts on the graph signal, and the U inverse is used to get the graph Fourier transform. And now that we have both the vertex and the graph frequency domain descriptions, we are now going to think about graph filters, where you are using some functions of the GSO, or the graph shift operator, in order to you pass a graph signal into the system, and then out you get another graph signal which has been filtered now. Um, and then I have so this graph filter can be thought of both in the vertex domain and in the frequency domain. And for the frequency domain, you take the graph Fourier transform, and similar to the Fourier properties in the time where the convolution becomes multiplication, here you have a similar idea. I
Sorry,
have a
Raksha,
yes.
yeah, you got a question from the chat. Is it
Yes,
okay?
I was just about to answer.
Okay,
Yeah,
perfect. Thanks.
yeah. So I was asked if the color of the nodes represents the values. Yes, it represents the values of the eigenvector, the corresponding eigenvector here. So I have, for this the figure, considered an unweighted graph. Yeah, and so the Laplacian just has the connectivity of this system. Uh, I hope that answered the question. Uh, with that, I am going to continue. So now we have an idea of what it means to filter a graph signal in the graph domain. But more frequently, we encounter signals which lie both in a graph as well as a time domain. You can think of this as signals or data on a graph that are time varying. And to express that, there is the concept of a graph temporal filter, which combines both the graph domain and the time domain descriptions. And so equivalently, you have a ZGFT, which is the Z transform and the graph Fourier transform combined or operated one after the other. And you can have a joint transfer function describing this graph temporal filter. And what is mostly interesting to this particular case study is the graph frequency autoregressive moving average kind of a filter, which is very commonly used, like the commonly used AR or ARMA filters. And here is the description of how this graph temporal filter operates in both the graph domain as well as the time domain. And we are going to revisit this part a bit later when we talk about power grids. So with this, there is another short, it's not a detour exactly, but a short description of a focus on low pass graph filtered signals. So what are low pass graph filter signals? These are the ones, if you pass a graph signal through a low pass filter, you are only retaining the lower frequency components. And this sort of implies correlation among data in the nodes of the and these nodal communities thus formed can be inferred using the sample data covariance matrix. We will also revisit this. Oh, I don't know why the figure is not rendering. Now we have it. So what I was saying here is we can focus on low pass graph filtered signals. And why are they of interest? Because we are trying to look at correlation among data in the nodes of a graph. And it so happens that when there are low pass graph filtered signals, their sample data covariance matrix is very low rank, and that's because of all this correlation among the data in different nodes. And this 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 equal this implication can then be used to detect or infer communities in the graph, and we will revisit this a little bit later. And so this sort of completes the initial part of what is graph signal processing. And with that background, we are now ready to describe what does it mean for GSP for the power grid. Any questions at this point? Okay, so I'm going to continue. So as I said before, why is GSP a natural choice for the power grid? Because electrical grid is an infrastructure network, and the graph here can be described by nodes, which are the buses or the buses in the transmission system, and the edges, which are the transmission lines. And the measurement data, therefore, then lie on this graph. And you can think of this measurement data as voltage or current data or power, so to speak. And these are electrical grid signals. And so the motivation for us is to find if GSP offers any new tools to analyze these electrical grid graph signals, and will such modeling help us solve some problems. And a figure here I show is the power network of a test case called Actives 2000, which we are using to validate some of our modeling here. And this is a synthetic test case developed for the state of Texas, just to mimic the grid of the Texas in US. And in this talk, what we are going to discuss is how we map our system models onto a GSP description, thereby getting a grid GSP framework, and how we can apply these GSP tools for anomaly detection and blind community inference. So what's the related work in this field? Of course, graph theoretical concepts in power systems have been explored quite a bit. There is also another detour, which is the graphical modeling, with graphical models, which are used for state estimation and optimal power flow and other different ideas. But the main thing here is that none of these works make any connection with GSP in particular. And there is another important part here, which is the empirical evidence that voltage and current measurements lie in a low dimensional subspace in the electrical grid. And this idea has been this observation has been used for anomaly detection and reconstructing missing measurements, etc. But the problem here is there is no explicit subspace known in advance, but we show that it's able to characterize this low dimensional subspace, and it is very much related to the GSP graph Fourier basis. And there was only one paper before us who were talking about detecting false data injection attacks using GSP. However, they just used this as a technique and did not go through any of the GSP modeling idea. So with that, let me enter into how we model or how we use GSP for the power grid. So what are the signals, first of all, that we obtain from the power grid? We can consider what are called the phasor measurement units, which extract complex envelopes of real voltage and current signals. And these are called voltage and current phasors. And one can consider a network of generators and non-generators, which are now the buses or the nodes in this graph. And then there is an edge set, undirected edge set, because power can flow in both directions. Uh, And we assume, or one can think of, that this phasor measurement unit or PMUs are installed on each of the nodes of this graph or on each bus. And then they give us a complex valued measurement with a particular amplitude and phase. And associated with this entire network is a complex valued Laplacian matrix. In this case, it turns out to be the system admittance matrix, which is denoted by Y most commonly in the power systems literature. And to deduce the GSP model, we are just recasting the Ohm's law for this transmission line network. And with that, so what is the GSP based generative model for the power grid that we come up with? So firstly, we consider a graph shift operator for the power grid. And this is the graph Laplacian plus a diagonal perturbation, which is just the generator admittance and load admittance values. Admittance is 1 over impedance. So that's the relationship here. And then then this graph shift operator has a certain eigenvalue decomposition, and we assume, or it's most commonly seen, that this is invertible. And therefore our grid GSP generative model is very simply the voltage graph signal is the output of a graph filter, which is described using this graph shift operator S, with the input being the current. So the input then is just generator current and load current. So overall, this is just a rewrite of the Ohm's law, which is current is equal to, or rather voltage is equal to admittance times the current. And very simply, then the graph filter here is just the S inverse, or the inverse of this graph shift operator. And this and this graph filter is a low pass graph filter. And why is that? Because of the inversion. So we are changing the ordering of all of the eigenvalues and how they act. And that's why this low pass graph filter can explain the low rank nature of voltage data. And here I describe sort of, if if we consider this graph filter which has been strictly low pass, as in we cut frequencies after a certain frequency value k, then what we get. So before I go into explaining it through a figure, what I plot here is the graph Fourier transform of a voltage uh, uh, graph signal. And on the x-axis, I have the graph frequency, which is normalized. And as one can see, the magnitude of this graph Fourier transform is higher in the lower frequency as compared to that of the higher frequency. Note that frequencies here are all graph frequencies. So this figure here is sort of the evidence, or just confirms our idea, that voltage graph signal is a low pass filtered graph signal. And so far we only discussed the graph input to a graph and output from a graph, input to a graph filter and output from a graph filter. But there is also an interesting temporal dynamic sitting in the input to this graph filter. So if I go back very briefly, so the generator current value that I am pointing, okay, I think I can annotate. So this part here has an interesting temporal dynamic, and this comes from the standard swing equations for the generators when generators are trying to match the load, and so there is a second order dynamics there going on. And what we are trying to model is the temporal dynamics of this ET, which is the generator voltages. Okay, I'm going to clear this. Okay. Oops. Yeah. And for that, however, one can see that this signal, this graph signal ET, is now described only on a subgraph or a smaller graph consisting only of the nodes or the buses which contain generators. So in order to describe their graph shift operator for the system, one has to consider a graph reduction. So a standard way of doing this is the Cron reduction or using the Schur complement. So what you do is now you have a reduced grid, equivalent reduced grid, and for that the generator only network GSO that we have is what we are defining as S red here. So this is on a space which is only, I mean, the number of nodes are now only the restricted to the number of generator buses in the system. And once we have this generator GSO, the GSP dynamics for this internal generator voltage is a graph frequency. I mean, this is a GFAR2 autoregressive with 2 taps process. And why 2 taps? Because of the swing equations, and that's how we derived it. And most of the details can be found in our papers that I just mentioned. What I want to point your attention to is this two-dimensional frequency response for this signal xt, which goes in as the input, which is transformed to give this et, or the generator voltages. So what I plot here is the time in the x-axis, not time, the time-based frequency, and then the graph frequency in the y domain. So it's two different frequencies and the equivalent frequency response. So it's sort of trying to visualize both in the graph domain as well as in the time domain, but both in their respective frequency domains, how does the signal look like, or what are the characteristics? And so that sort of concludes the modeling effort. Next, let's move on to sampling and reconstruction. So now that we have this particular theory is all from graph signal processing, not limited to the graph, not related to the power grid at all. I mean, not specific to the power grid. That's what I meant to say. So what is an equivalent band limiting operator is when you're only choosing certain graph frequency components of a graph signal. And that this band limiting operator is doing exactly that. It's a k frequency approximation of this graph signal. And similarly, a vertex limiting operator is downsampling in the vertex domain of a graph. So you're only choosing a few nodes on the graph. And that is using this vertex limiting operator. Now, the important question is, if you had only few measurements from this graph, and here I'm calling them voltage measurements because those are the results I'm showing. So if we had only few measurements from a few nodes on this graph, how well can I reconstruct the entire graph signal? And theory says that you need at least as many as the k frequencies that are important in the graph signal, sorry. And so the reconstruction then is very straightforward. It's a linear manner of doing so. And that's not sufficient, however, because you could choose any um, nodes of a graph, but you're not always going to have great reconstruction. Why is that? You need to choose these M placements of your measurement devices well, so that the system is, so that you can reconstruct better. And what is the idea of doing that? One of the optimal placing algorithms is to maximize the smallest singular value of this quantity here. What does it mean? That means you're choosing rows of this graph Fourier basis in the k frequency limited to just the k frequencies. And a way to do it is using a greedy algorithm. And the interesting part here is that the block structure in the graph shift operator places these measurement devices, or the PMUs, on different graph clusters. So you have, so let me explain this better with a figure here. So on the left, you see this is the GSO support of this GSO that I'm showing you. So you can clearly see the tiny clusters or the small graph clusters that this grid is organized in. And the placement algorithm tells you that you have to choose at least so many from different communities or clusters. Otherwise, you're not going to be able to reconstruct well. And here in this particular example, I show a placement of 100 measurement units out of 2000 overall nodes in this graph. And I've assumed a frequency cutoff of about 100. And on the right here, I show a reconstructed actual versus the reconstructed voltage after I place these PMUs. And as one can see, the loss is very little, even though you have very few measurement units in the system. And why is that? Because this is a very low pass graph signal, so all of its energy is concentrated in the with the k being as small. So the graph frequencies, the number of graph frequencies, the energy is localized to is very small. So that sort of shows you the results on sampling and reconstruction. That was one part of the application. So now let's discuss two different applications. One of them is blind. The next one is blind community inference. So as I showed in the figure before, power system topologies are organized as dense graph communities. And this is actually because of the population. So there are clusters of cities close to each other. So you have more dense networks there, and you have not so dense networks elsewhere. But this is always going to be a connected network. And this low pass nature of the voltage phasors helps in inferring or detecting these graph community structure. So the theory says that when graph signal is low pass, the top eigenvectors of the sample covariance matrix correspond to sort of the least eigenvectors of the graph shift operator. By top and least, I mean the ones corresponding to the least eigenvalues and the ones corresponding to the topmost eigenvalues. So what this means is this standard spectral clustering, which is performed on the Laplacian or some type of the Laplacian of the graph, and blind community inference are linked. So therefore, the algorithm to do them is as follows. You first compute a sample covariance matrix using these voltage phasors. Then you find k eigenvectors corresponding to the top k eigenvalues of this sample covariance matrix, and I denote them as u hat of k. And then, since this is made of both real and imaginary parts, you just take them apart, and then you apply the k-means clustering on the rows of this new matrix, and you are then going to get the community identification of each of the nodes in the network. And here I have a short, a small diagram. which is reproducing from a figure in our paper. So this is comparing the spectral clustering, which is the standard when you know what is the underlying graph Laplacian, to community detection when you don't know the underlying graph Laplacian, but all you have is access to a few samples of these graph signal or the voltage phasors. And as you can see, both of them tell you almost similar uh, story about who belongs to which community. So the big block here is the same as the one here. Of course, there are a few different associations as opposed to the one in the community direction. But overall, there is a good match between what is the actual community versus what we are able to infer using this technique. And all of this is possible because of the low pass nature of the voltage phasor, or the low pass nature of the voltage graph filter. With that, we move on to the next part, which is the anomaly detection. So since a graph signal that we are considering is low pass, anomalies are detected by high pass filtering. And volt so the voltage data under the null and alternative hypothesis, or when there is an anomaly versus when there is not, is as follows here. So this delta v here is an anomaly, and since it's not, and because it's an anomaly, so it's a high pass graph signal, so it doesn't appear in the same subspace as this graph filter has. And therefore, a way for detection is to high pass graph filter the and you can detect the false data injection attacks. That's one of the premise that we solve. And what we use is that the energy in high graph frequency domain implies an anomaly in the system. So the figure here I show is the magnitude of the graph frequency response uh, after high pass filtering. So when there is no attack or no anomaly, the energy in the higher graph frequencies, let's say after k equal to 1200, is low. As opposed to when there is an anomaly, you can see that the energy there has increased quite a bit. And this change is what we utilize to detect false data injection attacks. So that completes the GSP idea for the power grid. I'm going to pause here and ask if there are any questions. Okay. So, and how am I doing on time?
Yeah, if you want to leave some time for open questions, you should maybe wrap it up in like 10 minutes or so.
In 10 minutes. Okay. Yeah, then I have, okay. Thank you so much. So I have the time then to go through the next two slides that I have. That is to show GSP for two different types of data. So the first one I consider are the social network graph signals. And what are social network graphs? So there are, let's say, n individuals, and there are set of friendships between them, and that's expressed using this edge set. And there is a weighted adjacency matrix which can probably tell you how influenced you are or how close a friend you are. And opinions are then graph signals because everybody has opinion, and then this entire thing is evolving over time. And you have uh, two two parameters here, alpha being the trust, how much you trust your neighbors or how much you trust people in your network, and beta, which is the susceptibility to external opinion. So this is sort of a simplified evolution of opinions of people. And then in steady state, or as time goes to infinity, you can think that maybe everybody's opinion has saturated, and the output then looks like the output of a low pass graph signal again, with the excitation being the external opinion or external input xt. The figure here is just showing a social network graph for the US Senate voting records, and the red is the Republican, blue is the Democrat, and the purple ones are sort of in between. Let's say one senator voted one way and the other otherwise. And there is a nice paper here by uh, Xiao Xiao Wu, and this contains more details about opinion dynamics models for voting records. And it's kind of interesting to see this mimic be modeled in the graph signal, uh, like a graph signal. And the second part is one can think of financial data. So that can also be thought of as a graph signal. How? So let's consider a graph with, let's say there are n different institutions, and then there are business relation. They all have like they're related in business with each other. And there is again a weighted adjacency graph, which tells you how closely they're related. And say there is a business performance report and for a certain period, and that is what we can call as a graph signal, because each institution has its own performance report. And a model for how well you do as an institution is sort of a linear combination of how well your related businesses are doing plus some external factor, which is this xt. And even this system one can think of as, although this is inexact and it's not, it's still a very it's a hypothetical modeling. But what was interesting was to that we actually inferred business communities using the same community inference algorithm from stock data. And we saw that we were able to cluster these different institutions into real estate, information technology, energy, and stuff of this sort. So that's fairly interesting, but this is we have barely scratched the surface. So with that, I am going to conclude saying today we discussed the wonders of graph signal processing, especially the modeling part, and we developed GSP based models for the power systems, and we applied this for reconstruction, community inference, anomaly detection, and we also like briefly discussed some GSP models for social network and financial network data. And what would future work entail? For power systems, there's still a lot more GSP research to be done at the distribution level, where the network looks quite different from the transmission level. But in the overall context of GSP, one can always think of newer data sets and model them using concepts from graph signal processing. And when it comes to the tools of graph signal processing themselves, there is still a lot to be done in the area of directed graphs or graph signals, which can be described to be on the edge space as opposed to the node space, which we discussed all this while. And with that, I would like to conclude.